How is homework 2 going, by the way? You guys having a easy time with it? A little bit of a difficult time with it?
I only did question 1.
You only did question 1. Okay. What time is it? It's 5 o'clock. All right. I think he stepped out, so we'll just wait for him to come back real quick, and then we'll go ahead and start. All right. Well, since everyone, I think, submitted homework 1, I guess it's all right for me to upload the homework solutions. You guys want homework solutions, right? Yeah. Not that just the comments are all you get, but yeah. And then obviously we have office hours every day after class, so we could work on the homework questions if you guys wanted to. If you're having any difficulty with some of the questions or whatever, just had additional questions, whatnot. Yeah. You're back. Awesome. All right. So today we're going to continue our discussion of Chapter 2. I had a student or two message me this past weekend asking me to upload lectures ahead of time, so I'm going to do that, but obviously not going to upload the next lecture's PowerPoints yet, just simply because we're still in Chapter 2, and I think we're going to be in Chapter 2 for probably another week or 2. So, but thermal strain is the only chapter left that we still haven't covered that's technically on your homework 2. So that's going to be the one that's due this Wednesday. It's the one that's on your homework is not a challenging question. Once we go over it today, it should take you no more than probably like 10, 15 minutes to do it, if that. So introduction to thermal strain. Yes.
I got a question. So I was trying to access the recorded videos the other day, or today actually. And when I clicked on the link, it said like, it opened up like a separate page and was saying to use like my Outlook email for it. And I tried to sign in with that and it says it can't like verify and it doesn't think the account exists. I don't know if that's a problem with my thing or if it's a problem with like Brightspace and how they're on there. Did anybody else have a problem like that?
Are you logging in with your SUNY Suffolk email?
Yeah. I'm like, it would only give me the option to use my Suffolk email, and I clicked it, and then it still wouldn't go. So.
Can you show me after class?
Yeah.
Just because, I don't experience any issues. Does anyone else experience any issues with the lectures at all?
I haven't tried looking at them. Like, the first lecture you posted, it didn't have downloaded or anything, and I couldn't watch it.
Okay. All right. Yeah, Brightspace has been a pain in the butt this semester with it. In previous semesters, I've been able to upload it without any issues, so I don't know why it's
I'll just show
not
you
working.
I don't know, it might just be something I'm doing wrong.
If it doesn't work, I'll try uploading it to a Google Drive and then sharing that instead. Otherwise, I don't know how else to fix it. I might have to contact IT just to confirm the issue and what's going on. Any other questions before we hop into this? Any other concerns? All right, so we're going to continue our discussion of Chapter 2, specifically with thermal strain today. So, as you may know, as temperature changes with respect to time, materials will shrink or elongate respectively. You guys probably went over it in Physics 2 or Physics 3, if I recall, back when I took it. Which one?
Physics B is called.
Physics B, all right. So basically, you guys should be familiar with this equation where the deformation is equal to the coefficient of thermal expansion, which is a material-specific property, multiplied by the change in temperature times its initial length. Now, the strain is just whatever the deformation is divided by the normal length again. The only difference now is that this is for a thermal specific condition. So because of that, the thermal strain is just the coefficient of thermal expansion multiplied by the change in temperature. This thermal strain, unlike what we've covered previously, is not related to stress. All right? So just because a material elongates for thermal strain does not mean that it's under stress. The only time that it's under stress is if it's a statically indeterminate member, in which case then obviously there's going to be some type of compression or tension depending on if you have a temperature increase or a temperature decrease respectively. The stress arises from a temperature change unless the material is constrained. That's basically what I just said. And of course, the slides are already messed up. Awesome, let me check this. Just want to confirm. Here we go. I think that's not better. Thanks, Brane. That's the professor at Stony Brook. So length changes as temperature changes. I believe this should be using, that should be the delta is equal to, it should basically look like that. The strain was what we saw previously on the previous slides. So I'm just going to rewrite it all really quickly. So that should be what the blanks are basically filled. Of course, you can rewrite the stresses accordingly, not stresses, but basically, if you have a constrained system, like I was saying, you can basically use the deformation equation, PL over EA. When you set that equal to the deformation change that would arise from the temperature increase, it's basically the same thing as the statically indeterminate structures that we dealt with last class, where you apply an equivalent force. However, because there's no external forces applied, any force that's produced is explicitly due to the thermal change, which is why we get a stress equation that's got no force function within it whatsoever. So as a result, you just end up getting the alpha times the elastic modulus times the change in temperature. We can rewrite this to then just simply be like P is equal to negative alpha E delta T times A. Yes?
Is that, in thermal strain, is that alpha times T?
Yes.
Okay.
Yeah, my handwriting's atrocious. Sorry. The slides did not print properly for this one. So basically, the stress is just dependent on the elastic modulus, the coefficient of thermal expansion, and the temperature. And then to obtain the force, you just multiply it by the cross-sectional area of your given material. We have a negative sign because if you think about it, as you have a temperature increase, the bar is going to be expanding outwards. And what happens is you end up with a compressive force. You could think of it like railroad tracks. If you have a high temperature increase, what'll happen is actually those rails will actually buckle. So think of it as if you're solving a statically indeterminate structure again. You're just basically superimposing the deformation and then applying an equivalent force backwards. Do you guys need a minute to write this down or I'll... Yep. But everyone understands the concept of increasing temperature means compression, right? That's why we have a negative sign in the equation, because if you're associating a positive temperature increase, you're only going to get compression. Similarly, if you're going under a temperature reduction, there's going to be a tensile force that develops. Make sense? All right. Now, if we raise the temp... Now, let's consider just a circular rod. It has two separate components. All right, so this would just simply be, let's cut out a section just like this, and then we impose it to a temperature increase. Let's say that this material is of the same property. The circle will now fit exactly into the hole if it is compressed, if it is stretched, or as is without compressing or stretching. Wait. skip that. I don't like that slide. Yeah, I am not very well versed in half of these slides, so please forgive me. But I think a good example of this is also just with a composite bar. So I'm going to introduce the topic of what a composite member is. So this is kind of like your introduction of two different materials shared. Whereas here we had one different material, as you know, for one specific material. Even if you have two separate parts, everything will expand and contract within the same rate. So the deformations will be the same, which means you're not really going to undergo any type of stress. But once you have two separate materials, then you start undergoing some complications with the problem. So for a composite bar subjected to some temperature change, they have two entirely separate material properties. One of the things that you may want to consider is just the original bar length. And you might think with one of the ways that a composite would work is the two materials would expand and contract at different rates. However, what is a composite? A composite is two materials bonded together in order to share stress. You can think about it as if it was like a concrete column or a concrete beam. The steel isn't going to stretch or contract within the bar, right, because it's bonded together. They're going to deform at the same rate. So because of that, their strains are actually shared. And through this sharing of strains, we have to enforce some type of compatibility. So the way we do that is by just saying, all right, well, the deformations of the two materials in a composite bar have to be shared. And in order for them to be shared, there's going to be internal forces that develop to enforce this compatibility. So you'll notice for the tube, it's developing some type of tension force because the inside rod is obviously pulling on it. And then the rod itself is going to be compressed because the tube is pulling on it. All right? So one of the things that you ultimately need to do is just apply compatibility. That's expressed through this expression down here, where the sum of the elongations are basically going to equal each other. So a good way to think about it is that this deformation and this deformation here have to equal each other. And then once you calculate these deformations, those have to equal each other as well in order to be enforced. Another way I personally like to think about it is delta T is equal to delta T R. So those are your initial deformations. And then once you obviously plug in whatever deformation equation you're dealing with, in this case it would be the alpha L delta T equation, you can find how the two material properties relate to each other. Do you guys need a minute to write this down? All right, I'll let you guys write it. Let me see if oh, interesting. Did you guys see that? Oh, that's cool. I'm learning something new every day. And I don't know where I'm going with this. I'll just leave it. Let me know when you guys are ready to continue. Are there any questions so far about how the composites work? So far, we only just really expressed this in terms of temperature change. But if you had like a force, for example, that was pulling on this, that would be like this force P. You would basically just reapply the compatibility equations, but instead of using the alpha L delta T equation, it would just be PL over EA for each material. And then in that case, you would be able to derive separate equations for those as well. Does that make sense, what I just said? If not, I'll wait until we actually get to a good example. All right, so here's a good example. Entirely just ignore this right now. I will get to that really quickly. Basically, you calculate the change in lengths of each rod. At the initial temperature, the rod and the tube are unstressed, again, because we are unrestraining the system. So we are basically removing that reaction right there. From there, you calculate the elongation of each material, which then allows you to find the change in length of each material. That's expressed with that. My pen, this thing is not working. Come on. Whoops. All right. So for the thermal deformations, those can be just expressed using the thermal change in length equations, alpha delta T times L. That's for the unrestrained case with a temperature increase or a temperature decrease. From there, you then just apply compatibility by just replacing each material with its own separate internal force, which then gives you an entirely separate set of equations. So in total, you're going to have equations for the temperature changes, and you're also going to have equations for the changes in length due to the compression and tension within the bars due to the forced composite behavior. From there, you can use superposition similar to how we solve statically indeterminate members and just enforce the compatibility using the equations down below. After that, you're not going to be able to necessarily solve it right away. You need to enforce equilibrium. This compatibility is your second equation that you ultimately need in order to solve for the reaction forces. And once you apply that compatibility and the equilibrium equations, you can then just solve for the stresses within each of the rods. These are those really long equations that you see over on the right-hand side. Do you guys need a minute to write those down as well? All right. Let me just freeze this because I'm gonna see if I can't break this up a bit just to try and maybe try and express it in. There we go. And then this works obviously for some unlimited number of composite materials. So let's say you had like a rod here with, let's say, 3 different materials. All right. This inside here would be like material 1. Material 2 would be like the circular section here. And then material 3 would be the outside. So what you would ultimately do is just calculate the elongation that would be caused for each material. I'll call this material 1 and 1, 2 and 2, and then 3. Now, assuming that these rods stay the same length, you can say that the deformation in material 1 is the same as the deformation in material 2, which is the same in material 3. And then as you increase the number of materials that you have, you can have just some unlimited number of compatibility equations. For temperature changes, you would just use the alpha L delta T equation. And then obviously to determine forces, you would just use the come on. There we go. PL over EA. All right. Now there's another case. What happens if you have materials of 2 different lengths? This might be the case of, I don't know, let's say, I'm going to try and draw a neater sketch here. Like a rod here and another rod here. and it undergoes some temperature change. All right. Well, it's a similar thing, but just this time you would need to consider the lengths. Whereas in previous examples, if you have the length that's the same, these lengths can generally just cancel, which gives you the strain equations. So for this, it's the same thing, but the lengths don't cancel. Any questions about this? All right. So that was basically just thermal strain and thermal stresses. You guys should just be able to use the equations to be able to solve for your homework. The trick with it is just understanding what you're really kind of doing with the deformations, how the materials will kind of deform, and then understanding how the deformations will kind of relate to each other. Now we're going to go into Poisson's ratio. This is a type of material property that actually helps with explaining how structures deform in 3 dimensions. So consider a uniaxial tension of a rectangular rod here. You obviously are going to have a stress in one direction. That's going to be along the x direction due to the applied force. And because there's no forces applied in the y or z direction, the stresses in those directions are 0. However, even though you are not loading them, it doesn't necessarily mean it doesn't deform, right? Because if you think about it, you're stretching it. So what you'll actually get is maybe some caving in of this side here and some caving in of that side there, right? And then vice versa with maybe this top part will cave in like that and so on. So don't think that, all right? For homogeneous isotropic materials, we characterize it as Poisson's ratio. For composites, it becomes a much more complicated thing, honestly, outside the scope of what I'm probably going to be covering in this course. And Poisson's ratio we define as the ratio of the lateral stresses divided by the axial strain, or lateral strains divided by the axial strain. Another way of putting it is maybe just normal strain. So the strain that's in the regular direction where the load is being applied. Now you might be wondering, why is there a negative sign? The reason being is because if you undergo a tensile elongation within the direction the force is applied, then the lateral strains are going to be in an opposite direction. It's going to be compressing or shortening within those lateral directions. All right, so what you end up with is negative epsilon y over epsilon x equals negative epsilon z over epsilon x. So the strains, the lateral strains, are actually the same in both the y and z direction and not dependent on the length. What you will notice, though, is the deformations in the y and z directions will be different because they're different lengths. You can imagine that the strain equation is just the lateral deformation divided by the total length of that particular direction. So when you calculate the lateral strains, you can just multiply that by the dimension you're interested in, which just gives you the deformation. So what we can do is just say that the deformation in the y direction is just going to equal negative epsilon y, no, not negative. It's just going to equal epsilon y times the length in the y direction. And then epsilon z is just equal to, nope, not epsilon z, sorry. Whoops. Delta z is just equal to epsilon z times the length in the z direction. All right. And then obviously you can rewrite other expressions too. such as how the lateral strains are related to the stress equation. Simply put, just my recommendation is just always just solve for the lateral strains first and then just plug and chug everything else afterwards. Don't try and use those uniaxial equations just because they end up getting a little bit more confusing. So for generalized Hooke's law, and of course the image is not properly loading. You gotta be kidding me. I hate this PowerPoint. Let me see something. I gotta see if this thing is. Oh. Half of this was working earlier, so I will just be working from the OneNote. Hopefully this is displaying properly. Here we go. Yeah. Please excuse the technical errors. So for generalized Hooke's law for multi-axial normal loading, you can actually calculate a volumetric change. You might be wondering, why is the volume changing? You can think of it like on a molecular level, the molecules themselves are stretching, which is introducing minor gaps, which is why you get a relatively larger volume increase, even though it's actually a very small change. So what you can end up with is the volume change is actually just the initial volume multiplied by the summation of the strains. That just comes from this derivation here. You guys can take a minute to write that down too. And again, this is only assuming if the material is an isotropic or one uniform material. Now, if you have an incompressible material, meaning that the material doesn't change in volume whatsoever, a good example of an incompressible material is actually water or fluids in most instances. Then the strains are just going to remain constant, and basically all of the equations that we had dealt with are pretty much very similar. The only difference being is that the Poisson's ratio generally gets maxed out to about 0.5. So for incompressible materials, and I'm not going to be able to write now. So for incompressible materials, the Poisson's ratio is just 0.5. So I would write that down since I'm not marking it up on here because I'm having too many technical issues today. Let's see. I got to find like a new app just to figure out how to write all of this in. Let's see. Will this fix it? Just by opening it up in something else. No. Thanks. And yeah, it's just a repeat for incompressible materials. The Poisson's ratio gets maxed out to about 0.5. For many metals and ceramics, they range from 0.2 to 0.3. Stainless steel is like 0.27. Concrete actually usually maintains at around 0.2. And then for a Poisson's ratio less than 0, we call that an auxetic. That is a very interesting case. For those of you who are interested in transferring to Stony Brook University civil engineering, Professor Dr. Celli actually does a lot of research with auxetic materials. Basically, it kind of goes against intuition, where if you pull it out along one direction, everything expands. I actually have a video that I can probably try and find on my Google Drive to show you guys at the end of class if you're interested. But it's pretty cool. I sound nerdy though as heck in the video, so please don't judge me on that. All right. Now, you might be wondering what happens if we have loading in several different directions, sigma x, sigma y, sigma z. Well, the best way to really explain it is just take all of the uniaxial directions independently, and you can just sum them together, and you can just use superposition to obtain different directions. So this is the case for a uniaxial load, where if you have sigma x applied in one direction and then just to completely ignore sigma y and sigma z, you'll be able to get these uniaxial strain deformation equations, which is what I showed you guys at the beginning of lecture for when we started discussing Poisson's ratio. And then we can recall that the volume change is just equal to the change in the volume divided by the total volume, which is just the summation of the strains. We can use that sum there for the sum of the strains. We actually call that dilation. So that dilation parameter just helps define what the summation of all of the strains are. All right. You can rewrite it to then just say that the dilation is just equal to 1 minus 2 times the Poisson's ratio divided by E times the summation of all of the stresses. And then you can relate that even further to something what we call bulk modulus. That's that small term K, where once you apply the stresses all in one direction, or not one direction, but all uniformly in the same direction, in other words, hydrostatic pressure, then the bulk modulus can just be rewritten as the elastic modulus divided by 3 times 1 minus 2 times the Poisson's ratio. And that just comes from, again, hydrostatic pressure, meaning that the pressure acting in all directions is the same, both vertical and horizontally speaking. A good example of this would be like at the bottom of a dam. Now, it didn't give the equations that I wanted. This is kind of like where I wanted to go. I think the slides are out, but they're out of order a bit, but what I was trying to show you guys previously, ignore the shear stress strain relations right now. Just focus entirely on the left-hand side. But when you have stresses acting in all 3 directions, remember when I was just saying that for uniaxial loading, you get these equations here? Well, you can imagine that now if you have sigma z and you apply that uniaxially, you can rewrite these expressions in terms of the other parameters, right? All acting in one direction. So sigma z would equal sigma, or epsilon z would equal sigma z divided by E. And then you can relate the strains in the x and y directions based off of the applied load sigma z. I know I'm probably talking a lot, so please let me know if you are confused by this. Is what I'm saying okay? Everyone understanding? All right, so you keep doing that for sigma x, sigma y, sigma z, just all independently with each other. And what you can do is generalize it all into 3 equations, all dependent on sigma x, sigma y, and sigma z. All right, so the epsilon x equation is just equal to 1 divided by the elastic modulus multiplied by the stress in the x direction minus the Poisson's ratio times the stress in the y direction minus the Poisson's ratio times the stress in the z direction. This is basically just the equations rewritten to account for 3-dimensional loading. All right, you can actually do the derivation yourself. It's not too bad, but it's just a summation of the strains together. So epsilon x would just basically equal sigma x over E. This is considering the case if you had y stress loading and how it would contribute to the strain in the x direction, and then stress in the z direction and how it would contribute to the strain in the x direction. Does that make sense, what I'm trying to basically say? So those are ultimately just the normal stress strain equations for just a generalized 3-dimensional case. I'll give you guys a minute. Those 3 equations are very, very important, just for 3-dimensional loading. All right. So we've got some Poisson's ratio for common materials. I'm not going to ask you guys to write this down. Generally, I will either give it to you, I will give you a table with some Poisson ratio materials, or worst comes to worst, you can generally find this stuff online. It's openly available to you. There's plenty of engineering toolboxes that give you these material properties. Same thing with elastic moduli and coefficients of thermal expansion. They're material properties. All right, so we've got a good example right here, which let me just see if I can't open this up and maybe try and not use that. Or is this going to be an absolute nightmare? There we go. Now it's working. All right. So I'll walk through this one step at a time. I just didn't want the entire solution shown up there. All right, so for this example, this is one of the cases where it's subjected to uniaxial loading. This would follow a sign convention where y is in this direction, x would be in that direction, and then z would be like into and out of the page. All right, so for the stress in the y direction, this sigma x is actually just a uniform stress that's being applied vertically downwards. So that stress is 62 megapascals acting in compression. Now, from that compression, is the material going to shorten or increase in length? What do you guys think? Hopefully everyone can see that it would shorten in length. Now, for a brass cylinder, you guys would probably also say like the material would expand outward. It's going to be a very small lateral expansion, but obviously it will because of the Poisson's ratio that we have to consider. So Poisson's ratio is defined as that 0.33. We're given an elastic modulus of 105 gigapascals, and we're just basically asked to find the change in height and change in volume of the cylinder. So we know from the problem statement the stresses in the x and the z direction are 0. The stress in the y direction, we can write that in terms of pascals, so we get negative 62 times 10 to the 6 pascals. And then we can rewrite the stress in the y direction, or the strain in the y direction, using that general equation that I had pointed out earlier. That's the 1 over e times negative nu sigma x plus nu sigma y minus nu sigma z. All right. Now, since sigma x and sigma z are 0, what we're left with is just epsilon y is equal to sigma y over e. That's just your standardized equation for strain in one particular direction with one particular load. So once you plug that in, you get a really small strain of around 590.48 times 10 to the negative 6. Again, strain is a unitless quantity, so this would probably be in units of like millimeters per millimeter or meters per meter. And then just to find the change in the height, you can just multiply that h naught, the initial height of 135 millimeters, times the strain that's undergoing shortening, and you would find that the change in the height is negative 0.0797 millimeters. Now, what if we wanted to find the lateral change in radius? How would we do that? That's not in this slide, which is why I am asking that. What do you guys think we would do if we wanted to find the change in the radius? Or the change in diameter is a better one. Yes, Andres. Okay. That would be something. Let me first ask this. What is the strain in the y and the z direction? How would we solve that? Yeah.
It's a negative Poisson's ratio times the strain in the x direction over the modulus or e.
It can be, yes. But the thing is, we already calculated the normal strain, so you don't even need the stress and the elastic modulus. Because we're actually already given the strain through this term here. So the strain in the y direction is just going to be that negative Poisson's ratio times the negative 590.48 times 10 to the negative 6. And again, what I was trying to point out earlier is the strain in the y and z direction. It's the same thing because the length that they're associated with is entirely independent of the strain. So this is actually just the same as the strain in the y direction. The change in diameter is also just conveniently the same because it's a circle. If it was a rectangular shape, then to find the changes in length of those two sides, you would need to consider the length of the material. But the strains, laterally speaking, would be the same no matter what. All right, so let me just grab my calculator real quick because I don't know what this value would be off the top of my head. So 590.48 times 10 to the negative 6 times 0.33. And what we get is a lateral strain of 1.95 times 10 to the negative 4, which that gives us 195 times 10 to the negative 6. And then to find the change in the diameter, that would just be the strain, the lateral strain, which would just be that strain that we previously computed, epsilon y, epsilon z, times the diameter of 85 millimeters, which will give us a lateral change in dimension of 0.166 millimeters in diameter. You'll notice from the math, that's a positive value, which is important to note. Any questions so far about that? Write it down because I'm about to clear it, so that way I can continue with the change in volume question. Yes?
I missed it. Can you explain about what's that, epsilon L? Or is that Z?
Epsilon L, I'm just using that as a subscript for lateral strain, because what I was trying to say is the strain in the y and z direction are just the lateral strain, all right? It's not necessarily a direction-dependent thing, except the fact that it's just laterally speaking. So that's all I was trying to say with that. So that's why I like to just generalize lateral strain, not to a particular x or y direction, but just say lateral. But you guys can do whatever you want. Good to continue? Awesome. So let me clear that. All right. So to find the change in the volume, first you just need to find the initial volume. And then from there you can calculate the dilation that would ultimately be undergone by the given material. That's just using the plug and chug equations. Again, the sigma x and the sigma z are just equal to 0. So that gets rewritten as that 1 minus 2 times the Poisson's ratio, all multiplied by the stress divided by E. So another way of writing this would just be 1 minus 2 times the Poisson's ratio times that epsilon y value, which is what we calculated previously. Throwing that all into the equation, you get that the total dilation is negative 200.76 times 10 to the negative 6. And since now we have the dilation, we can just multiply that by the direct initial volume, and that'll give us a volume change. Now there's another way that you could do this, all right? This is not the only way. The other way that you can do this, I'll let you guys actually finish writing this, and then I'll show you guys the other way. The other way is a little bit longer, but I like personally doing it because I like to think that it's a little more intuitive. In the meantime, I will actually hand you guys. Carlos, right? Yes. Oh, nice one. All right. Now, the other way that you could have done this is, first of all, just calculate your initial area, your initial volume. We calculated what the normal strain was, and the normal deformation is just this delta H. So this is just your delta. What was the lateral deformation that we calculated previously when I was doing it by hand? 0.9.
It was the epsilon alpha.
I think it was 0.0166 millimeters.
Oh, yes, sorry.
Yes.
Yeah.
All right. So from there, you can calculate final dimensions. So the final height would just be 135 millimeters minus the 0.0797 millimeters. That gives you 134.92 millimeters, give or take. You then calculate the final diameter. So that's just going to be the 85 millimeters plus whatever you calculated, the 0.0166 millimeters. That should give you 85.02 millimeters. And from there, you can calculate a total final area. So that's just pi over 4 times 85.02 squared. And then your final volume is just going to be that AF times HF. And theoretically, obviously, I'm going to have a really gross amount of round off error because I'm not using all of the very precise numbers because I only rounded it to 2 digits. But in theory, what you should get is that same volume, which conveniently I am blocking, of the 153.8 millimeters. So that's just another way that you guys can go about that if you don't like working with the dilation parameter. So 2 different ways. Dilation just makes it easier because it's just plug and chug, but if the other way is more intuitive for you, go for it. All right. What time is it, by the way? I just want to make sure I'm good on time. Oh, still got half an hour. All right. So apart from the normal stresses and normal strains that we've been dealing with, we also have shear strains. Shear strains are obviously parallel to the cross-sectional area, as we had previously discussed. And this shear strain is ultimately going to cause some type of deformation that's lateral. So shear strain is just going to equal, of course, the symbol is just all messed up again. But to represent shear strain, we use a Greek letter, gamma, and then your shear stress is just that tau xy. Now shear strain is just equal to that gamma xy. The convention shown is obviously positive. Hopefully you guys remember from when we were going over chapter 1. Positive sign convention is all dependent on where the coordinates are going. So, for example, stress is positive x, stress is positive y. So the shear stress is just going to be positive when you multiply positive times a positive. Right. From here, I am just going to just change to this. But basically, for small linear elastic deformations, the shear stress, xy, is just going to equal that term g times gamma xy, which is your shear strain, which is all dependent on a lateral loading. That is basically this term here. So let me just zoom in on that again. So one of the things that we can do is just, obviously the shear strain is all just going to be half and half. It's going to be split between the 2 directions. So if we rotate our shape, we can actually sum it to one particular shear strain acting in one particular direction, just to make our lives a little easier with the calculations. And then considering some distance, delta x, and stupid thing. I really got to work on these slides a lot better. Basically, just consider the geometry of the deformation. You would find, using small angle approximations, that the shear strain is roughly the angle that's basically computed. And that term G is a material property known as the shear modulus, which is entirely different than the elastic modulus. The elastic modulus and the shear modulus are related through the Poisson's ratio. I think it's expressed on one of the, it's expressed on a future slide. But again, that shear modulus is a property defined by the specific material. I think I'm going to give up on these PowerPoints in the future because I am officially now getting aggravated that none of these things work. But, yeah. Let me see. Unless I can somehow manage to just get this all to, like, be expressed in a different slide or PowerPoint. Maybe it's in, like, Google Slides. I don't know. But, yeah. We could go over the deformation after class if you guys want, but I'm now at a point where I'm just officially aggravated at this. All right, let's work on an example together just to show you guys how shear strain would ultimately look like. You can consider the plastic block shown. So this, it's basically just a gray block that we're looking at right now. Don't look at anything with the blue. Basically just assume that the blue is just a very rigid material and that gray area is a plastic block that we're considering in our design. This force P that's located over on the right hand side is a 63 kip force. And we have our term G, which is our shear modulus, which has a relatively high value of 150 kips per square inch. And what we want to do is determine the deflection of the plate. So, from the previous slides, we determined that the strain in the that the strain in a particular direction is just going to equal gamma is equal to the deformation multiplied by the length, which is also equal to not the normal stress, but shear stress divided by shear modulus G. All right, now, really quickly, what is the shear stress going to be? What's the area that's subjected to shearing? Well, if we draw out a little sketch, we know that the shear stress area is just going to be that little back surface, right? Because that's the area that's parallel to the force, which gives us an area of what? 3.2 times 4.8 inches, right? So we take that, and what we get is an area subjected to shear of 15.36 inches squared. And simply put, we can calculate what the shear stress would be, which is just going to be 63 kips, divided by the 15.36 inches squared, which gives us a shear stress of around 4.102 kips per square inch. All right, now we want to find the deformation. We can compute the lateral strain by just saying 4.102 KSI divided by the shear modulus of 150 KSI, which is just equal to 0.027. And again, it's a unitless quantity. This could be inches per inch if you want to really write that. But now here comes the question that basically the last slides were too broken for me to express, is what is the length that we consider? In other words, this length here. So, when it comes to anything shear related, think exactly the opposite of normal, right? So for normal stresses, the parallel length to the force was the length that we use for deformation. So using logic of everything is opposite for shear, you use the perpendicular length in order to determine the deformation. What is the perpendicular length to that force P?
Would be just 2 inches.
Exactly. You would use the 2 inches. So to find the deformation, it's just going to be the lateral strain times that perpendicular length, which is the 0.027 times the 2 inches, which gives you a lateral deformation of around 0.055 inches. Now, another way you could have done this is just rewriting all of the equations. If you guys remember from when we dealt with axial loading, we calculated delta is equal to PL over EA. Well, if you follow a very similar logic to shear, where all of the terms are synonymous with each other, you can actually just calculate that the shear deformation, which I'm actually going to subscribe with V, is just equal to whatever your shear force is multiplied by your perpendicular distance divided by what's the material property that we're considering, G, the shear modulus, and then the area subjected to shear, AV. Yes?
We're not using the blue piece, right? But if we were, the length would be bigger, right?
Not quite, because then you're dealing with two separate materials. We're only considering the lateral strain of the gray block itself for this example.
Is P acting like on the outside face of the blue piece?
You could think of it as acting on like the center.
Between
And
the two
it's,
of them?
yeah, so
Okay.
think of it like the blue is like an infinitely stiff material, in which case then the force is just directly transmitted directly to the block, and the blue is not undergoing any type of strain. Otherwise, if it was a softer material, something that strain you would want to consider, then you would need to just sum the deformations together. But in this case, the problem doesn't specify what the blue would be made out of. Does that make sense with how I kind of correlated the equations together? If you guys just use the shear stress and strain equations, you can come up to this expression pretty easily. All right, and you can see here they took a similar approach. They calculated the shear stress, and then from there just calculated what the shear deformation was, knowing that the perpendicular distance L, or what they call H, is just what they needed to compute the lateral deformation. Any questions about this example? No? All right. So, and again, these lines are messed up, so back to this one. So in general, and let's see if I can't grab it. There we go. So these are all of your expressions. So we went over the normal stress and strain, and now for the shear stress and strain, we could just generalize it in three directions. But one of the things you'll actually notice is the shear stresses in the XZ and YZ direction have no impact on the stresses in the XY direction. That's because the strains are just entirely lateral and they don't really contribute to any changes in length. They're just geometric changes. You can think of it as if you had like a really large textbook and you pushed it up on the top, all the pages would just kind of skew. So there's no volume change really associated with it. All right. All right. Now, back to what I was saying about the materials being related to each other. Basically, E and G, they're both material properties that are related to each other. Let me see if these slides work. Again, now. Please work. All right. So, to find the relationship between the elastic modulus, the Poisson's ratio, and the shear modulus, we need to consider a very small block of some unit dimension, so 1 inch by 1 inch, we can say. Now, when there's a lateral strain that's subjected to it or a normal strain, then the dimensions change respectively to 1 plus the unit deformation, and then 1 minus Poisson's ratio times the unit deformation. That's what the Poisson's ratio times epsilon x is that's just your lateral strain. You can then just sum that up based off of particular angles. That would just be the pi over 2 or 90 degrees plus whatever your shear strain is if you're orienting it a certain way. And it doesn't work. Basically just messing around with all the angles and the geometric configurations, you should arrive to a conclusion where the shear modulus is just equal to the elastic modulus divided by 2 times 1 plus the Poisson's ratio. All right, that's how everything is basically related. Whenever you guys are looking at material tables, you will always find that this relation holds true. All right, I will give you guys a minute. I'm not going to be testing you guys on the orientation or the derivation of this whatsoever, but what I will ask you guys is just to remember that boxed equation there, because that's a really important one. All right. Now, going into 2.10, we're going to start discussing about St. Venant's principle. Now, previously, what we have been all previously looking at so far is when stress is in a uniform concentration. Is this true? Not exactly. Stresses will actually concentrate locally depending on where the loads are applied. If you guys ever played with any type of like structural analysis modeling software, you guys will actually see sometimes like stress concentrations located at particular points because of the fact that St. Venant's principle is able to be modeled accordingly. So, as a result, that's why you get larger stress concentrations around the points. The stress concentrations generally tend to reduce as distance increases because of the fact that the stresses get distributed relatively fast. So this is like a good example of how the stresses distribute. If you have a force P that's basically applied to both points within a rectangular tube, the stresses close to the point of application are very large. In this case, the maximum stress is around 2.575 times the average stress that we would consider, but the minimum stresses are really small around the outside. And then as you move further and further and further towards the center of the rod, the stresses become more uniform, which is why we generally make the assumption of uniform stresses. Now, you might be wondering, why don't we always consider the maximum stresses? It's because it's relatively hard to model it, especially with particular geometries. And also because a lot of times, especially for those of you pursuing civil structural engineering, material yielding generally kind of takes control, which then allows for a redistribution of stresses. So because of that, that's just another thing that ends up making things a little more complicated. For stress concentrations, this would be for stresses around particular openings or around chamfers in a particular rod. I'll give you guys these tables, so don't worry about sketching out the tables because there's like probably 50 of them that are dependent on the material, on like the type of loading, the geometry. But ultimately, you can find the stress concentrations around particular points. For example, around an opening, the stresses around the opening will actually be somewhat larger Let me see if I can't actually pull that up now. Let's see, can I show you guys how it would look? We went over this slide. So stress concentrations, I actually think I skipped this slide. I mentioned that the stresses around openings will be larger. That's because there's going to be more force concentrated to those, and you'll notice that the hole generally want to become deformed. So the way that you need to find these stresses is by using these factors K. This factor K, which again, there's a bunch of tables to determine this. This K term is just the maximum stress within the material divided by the average stress, which you would just rewrite as the maximum stress is equal to K times sigma average, which sigma average is just going to be that force P divided by the gross cross-sectional area of the material. That A is just going to be of this, because obviously you don't consider any area from the hole whatsoever, right? Because that's not carrying anything. So how does this work? Simply put, if you were given some geometric properties like the radius of the circle, you would then just figure out what this term is, 2r over d. Let's say you got it around 0.4, you calculated it because the geometry of it will be given. You would just take that table here, just move it upwards vertically, up until you reach this red line over here. And then from there, carry it across until you calculate your value K. And then from there, you can figure out what the maximum stress is at the particular point. And that's applicable for anything, for all of the stress concentration tables. It's just a matter of what terms you're supposed to be looking at. Now, one thing you'll notice is, again, the stresses vary relatively quadratically, so it's very hard to kind of figure out. So this is basically St. Bennett's principle. All right. I am going to go over a quick example. I'll upload like tables just outlining what those stress concentrations would look like for different conditions. Maybe I'll print them out and give them to you guys, but you guys will have that information. So, oh, here's the table. Yeah. So for this problem, we're asked to determine the largest axial load that can be safely supported by a flat steel bar. And we're asked to consider basically the stress concentration around the bar. So what we first need to know is we need to determine the geometric ratios. You'll notice that there's actually different plots for different conditions. So you can imagine now we need to calculate R over D and D over D because we have different plots, so we need to figure out what plot we need. So calculate capital D divided by lowercase d. What we end up with is this D here is 60 millimeters. This here is 40 millimeters. 60 millimeters divided by 40. Which gives us a ratio of around 1.5. So that tells us that we want to be using this figure right here. All right, from here, we want to figure out the ratio of the radius, fillet radius, over that small dimension D. The fillet radius was defined as 8 millimeters divided by 40 millimeters, because that's what D is. And we get a ratio of around 0.2. So from there, we take our point, drag it up until we reach our diagram of interest. That is going to be that point there. Let me do this in blue. 0.2. And then we just got to drag this across. Obviously, it's a very gross sketch, but we get that our stress concentration K is approximately what, 1.82? It doesn't need to be very precise. Granted, there's computer software that helps you iterate it a little bit better, but as long as you're working by hand, I'm not going to judge it too much if you're off by like 0.05 or something like that, 0.1, you know. All right, so from there, we would just take the average stress and multiply it by that K value to obtain what the maximum stress is. Now you'll notice in this case, the maximum stress can't be any higher than 165 megapascals. That's the allowable limit of the material. So that's what the sigma max becomes. So 165 megapascals is equal to the 1.82 times sigma average, which is just going to be our applied force divided by the cross-sectional area, A. What is our cross-sectional area, A? Our area is going to basically be the 40 millimeters times the 10 millimeter thickness that's defined in the problem here. Reason for that is because the stress concentration is going to be occurring at that location specifically. Obviously, it's a smaller dimension, so you want to try and use as small of the dimensions as possible. All right, so our cross-sectional area becomes 400 millimeters squared. 165 megapascals, that's 165 newtons per millimeter squared, so our force is going to end up being in newtons. So rewriting all of this, 165 divided by 1.82, multiply that by about 400 millimeters squared, and you get around 36,264 newtons. You guys see how I get that? Awesome. I'm going to erase it and then just show you guys what it came up with, which should be around the same thing, depending on what they used for K. All right, we clear that. Yada, yada, yada. They did the same. Oh, they used K is equal to 1.82. And yeah, they got 36.3 kilonewtons. What time is it? Let's do another example now. All right. This time, I want to see if you guys can actually do it by yourselves. I know the diagram is a little bit tough, but yeah, give it your best shot, as best as you can. I just realized this question is a bit ambiguous. There's no dimension. All right. So the way that this problem is basically worded, it's basically asking you what size the hole needs to be in order for the stresses to be maximum. So you can think about it that the maximum stress for a stress concentration would basically occur around this point here. So the maximum stress concentration that we could get is around 0.3. That's, we assume that because we're assuming an infinitesimal hole, so that radius becomes really, really, really small as a stress concentration. So by saying that our K value is equal to 3.0, we can then just calculate that sigma max is just equal to sigma average times our K value, which is just 3 times the average stress. Now, yielding is first going to occur right around that tiny microscopic opening. So we would then say that sigma y is just equal the yield strength, which is the maximum stress that's allowed by the material, is just equal to that sigma max, which is just 3 times the average stress. All right, which means 3p over a. So if we wanted to find what force this would be occurring at, it would just be the 1 over 3 times the yield stress times the cross-sectional area. And then that's basically the force in which yielding would be occurring. Does that make sense? Sorry about that. And then, of course, the slides are messed up because you can't have a good lecture without messing up with the slides. All right. That is going to conclude today's lecture. Next class we'll go into plasticity, which is a fun one. I will try and find a workaround for the PowerPoints because I am now at a point where I am getting aggravated at the crappy presentation that this has become. But I hope everyone is understanding the material. If not, I will have additional office hours after classes where we can kind of discuss and I can try and do it on a better scale. Yep.